seen him before. If you haven't, definitely check out his website or re-listen to last night's talk from Mud, wherein he was mentioned.
That was kind of nice.
And hopefully we're ready to go with taping. So enjoy.
Hi, everybody. I'm Scott Moulton. Most of you might have seen me before if you've been to Shmoocon before. I want to thank Shmoocon for having me back again. This is a little bit of a different talk for me from a standpoint of, well, it's still about hard drives, so you don't have to worry about it being that different. But it's more mechanical in nature. You know, typically I attract a couple of things with regards to logistical recoveries and doing some logical. This one's pretty much all physical at this point. I'm addressing a more recent problem with hard drives, spindle replacements and platter replacements, and some unique problems that have occurred. Also, a little bit about my presentation. As you guys know, I kind of try to stay on the edge. If you've seen, how many people have seen a presentation I've done before? Okay, so as you know, I try to do animations in most of mine. I have a few that don't have any, but the animations take on a life of their own every time I do them. There's been occasions where I've written animations a year in advance because we have to go through this process. If you've seen my other ones, they're basically done in Flash, and so we don't normally use PowerPoint or try to do anything with PowerPoint. So we have to have our own framework to present them because there's just not enough. Flash is basically meant to do these little small things, 10, 15-second type clips or whatever. So when you try to do a 50-minute presentation, it's a major undertaking. So again, I'm switching complete platforms and trying to do something a little bit different. I have a friend, his name is Michael Tilson. He's done a fantastic job working with me on doing some animations. He does short clips, videos, short commercials and stuff, but it's different than what I've done before just dealing with Flash. He actually does, true movie type stuff and true movie clips. And so when I sat down with him, I sat with him about 2 months ago when I got accepted to Shmoocon. I said, look, I'd like to do some animations for this. I usually try to do like a whole hour of animation, but can you help me out with this? And he goes, yeah, sure. He goes, basically, and maybe some of you guys don't know, but when you render animations, it takes about a minute a frame. So there's 30 frames in a second, and then 60 seconds in a minute, and so on and so on. So I said, hey, look, can you help me with this? We have about 2 months. I'll write the script, and you put this down. And he goes, okay, great. How many minutes do you need? And I said 6. And he goes, 6? How are we going to render that? So I have almost 6 minutes of rendering in this presentation. It's going to take every minute of my life to try to complete this entire speech in animated form. So you'll actually see quite a bit of animation. We had this going all the way up to like Wednesday, Thursday night before I flew out here. So it's a little rougher. I do have a lot of photos in here also that will be from my diagnostic side. So you'll see some while I'm actually building a process. So I'll explain this process to you and go through this. First thing is I'm also a member of the staff of Outer Zone. If you guys know what Outer Zone is, it's a conference in Atlanta, and it will be March 19th of this year. So we have Outer Zone coming up. And then Skydog Con. Skydog and I and Robin and Amy are members of this, so there will be Skydog Con towards the end of this year. So you'll see some new presentations. There may be additional animations for me on this particular side. So my goals for this speech, basically at this point, there's a new problem having to do with the bearings in a hard drive and what actually happens when you have a hard drive and the spindle seizes. How many people have had a hard drive that the motor just doesn't turn and it just seized? Yes? It's starting to happen very frequently now. Externals, USBs, whatever. Larger hard drives are getting worse. There's a new mechanism that's basically gone in place in the last 2 or 3 years, and the platters are much heavier than they used to be. So now the spindles are basically breaking, the bearings are basically breaking in the process. So my goal for this was basically to attack a way of replacing these seized bearings and to do something else with it, trying to do it as cheap as possible. There certainly is an expensive way to do this. There are tools that exist. There are things that you could do that are in excess of $5,000 or $6,000. There's a few kind of unique ways I've seen people trying to do this, which are, using tape and then flipping the drive over and everything falls out and then they try to reassemble it. Those are a little more questionable on whether or not their success rate is high or not, but certainly possible. So again, there are tools that are like in excess of $5,000, but that doesn't help people either A, understand this process, or B, do it themselves. There's a lot of people I've spurned on to create a company, do something, who just don't have $6,000 for one little tiny small process because it doesn't address any of these other processes that have to go on. If you've seen my other talks, this is an epic. Basically, if you look at all my other speeches, they'll talk about things like the head replacements and the boards and how to fix them and logical recoveries. This is just one in that whole piece. So when you watch the whole thing, so you'll still have to go back and address head replacements and things like that. I'm not going to cover that part again. So the whole point is to do this as cheap as possible, trying to stay $100 or cheaper, and try to get this done with local things that you can actually pick out for parts rather than having to go down to someplace and have them mill a part for you. So I know you guys can appreciate the do-it-yourself kind of response here that I'm trying to do. So, and I'm hoping that this is the kind of thing that some of you will at least attempt, maybe even add to my tools, publish it, feel free. So we're going to make kind of our own tools. We're going to go through replacing these bearings, and we're going to disassemble a drive. Now, the hard thing here in this whole presentation is that it's going to be a little bit redundant because the process has to be done 3 times in order for the process to complete. So you'll see a couple of things that repeat as we go through donor drive and then to a complete drive. So it does have to repeat. Basically, this is just kind of a quick summary of money that I spent in order to accomplish this. Now, I've spent about 2.5 months trying to do development on it to get it smooth, and it's coming along to almost be perfectly smooth. But basically, at this point, it's roughly $100 or so. You're going to need an arbor press that you can buy at like your local Harbor Freight or something along those lines. Digital caliper, which is only about $15 there. A punch set, which actually you'll need a punch set and a drift set. So you'll actually need punch and a drift, which you can actually get all in one combined package for like $30. And then we're going to use a broken hard drive to make our parts. Dremels and a saw, and then some pressurized air. This is kind of where the situation starts. We've had this tool. You guys have seen this in my previous presentations. It's called an HPE, which is a hard disk platter removal exchange tool. So you're doing an exchange of one set of platters to another when you have a seized motor. The idea is that the motor doesn't work, and so in order to actually get a working motor, you don't really replace it. You actually pick up all the platters and you move it to a working one. And that makes sense. It's very quick and easy. It's easy to do with this tool. This is a fairly cheap tool by comparison. I call it the coffee can, but it's about $600 to $700 for this tool. So you can get it done. Even kind of a do-it-yourselfer can still get it done, but there's other ways to get it done. But this tool doesn't work on some of the newer drives. So let me explain what some of the newer drives are and what actually happens. This only took about a month. Wednesday night. So this is the HPE trying to go down over the platters. And when it tries to go over the platters, you'll see that there's this black area on the left that is basically a spacer, is what we're calling it. It's an acoustic spacer, supposedly, but it also helps to increase the airflow in between the platters so that as your heads are approaching this area, the heads actually will fly higher over the platters because there is more airflow in that particular area. Stops some vibration. It does add some weight to the drive. These particular ones I'm showing here are plastic. So at one point in time, we had some luck kind of using some plumber's tools to like heat up a wire, cut around the plastic, take it out, and then we could remove the platters. But with this, we are not able to use our tool and lift it up. But what has happened is, so this plastic one, you could kind of cut off these lips. There's 3 areas that the lips basically mount inside of the casing of the drive, and I'll show you those. But what happened later is they switched to metal. So now a lot of these are metal. And so those ones on the right-hand side where you see those screws, there's a screw that would go through them, and then there's 3 locations that goes all the way around the disc. Those stop us from moving the platters. We can't take them out. There's just no easy way to do that with our previous existing tools. And it made a very simple thing that we did as data recovery people a very complex thing. Because there's been like, over 2 years, there's been a lot of people that have been trying to develop a way to do this. And there are some other HPEs that have special cutouts, so you can like clamp around the disc, but they've all kind of been crappy. They don't really work very well. The platters sometimes fall out after you get them out or something like that. So that kind of blues. So this is what we're looking at. This is the pattern, this is the basic idea for what we actually have for the spindle that holds the platters on the drive. Now, this area that's dotted on the outside, that's basically where the platters are mounted. They're mounted on this outside ring, and they sit in this ring. This centerpiece that's red is what we're focusing on, including the area where in the middle there where it's kind of rigid and stuff. This is actually the bearings. This is what is called fluid dynamic bearings. That's the component that we're focusing on. Now, outside of that, there would still be the outside casing of your drive. So basically, the bottom of the fluid dynamic bearings actually sticks through the casing on your drive. And you would see this on the bottom as a little silver, looks like a little silver nickel on the bottom of your drive. So that's the piece that I'm focusing on here. This is what it looks like when you remove it. Now, getting it out is an extremely difficult task, way more than you would ever believe it should be. So that's what this process is all about, is why we're dealing with this bearing. So why does this bearing seize? Basically, this is what it looks like when you kind of get it out. And on the bottom there, you will actually see the coils themselves. This is actually around the top of the spindle, there's magnets. There's a circle magnet. And when power is applied to the coils on the bottom, it causes the magnets to push, basically spin, kind of like a speaker does, causes it to vibrate so you can actually hear sound. That's exactly what happens here. And so everything has to flow very smoothly on top of this bearing. The bearing has to be able to turn. Well, the only thing that turns in this bearing is that center pin. The silver center pin is the piece that actually moves. So this is what it looks like inside. Ooh. All right, so in this particular case, you guys know about ball bearings and a bunch of other things, and I'll show a picture of those in a minute, so those of you who don't know. This is basically what your drive is spinning on. There is a post that goes through the center, and then in that post itself, there is basically a little copper ring at the bottom. And then below that, there's kind of a cap that seals this whole thing with pressure and with some fluid inside of it. So the fluid basically is what is known as the fluid dynamic bearing. I'll explain that. And now we will put it all back together. It's a little slow on this animation, didn't have enough time to time it. But it basically all goes back together, and then that little pin that sticks up through the top is actually where the platters physically are sitting on top, and that's actually just pressured into the actual top of the spindle. There's no screws or anything around this. This thing is actually just pushed in at a high end, like 2 tons of pressure, to get it smack into the middle of the thing, and then it's held there in place in the middle of that ring. The other screws that are there that you see, when you take those screws off, it's kind of dark on that screen, but when you take those screws off, the platters just fall out, basically. They're all loose. There's a ring in between them that has no grid or anything on them to basically keep you aligned. And if you misalign these platters, then you will not be able to recover your data. They basically have what's called servo information that is through all the platters, so they all basically are aligned, and your data is actually sitting in the correct location all the time. And if you just took those screws out and flipped it over and you took your platters out, that's it. It's over. End of, and we can just walk off stage here. So that is what we're trying to keep intact, which previously with the HPE, the thing that would sit around it, would actually snap around it. We'd be able to take those screws out and just pull the platters out. We wouldn't have to worry about it. So when you pop this thing apart, this is basically what it looks like on the inside. This is actually a real picture as opposed to my animated picture. So this is actually while I'm actually doing some discovery on this particular component. So when you're looking at your bearings, when you're looking at your choices, prior to, say, 2003, 2004, we used ball bearings. And ball bearings are basically at the top here, you'll actually see there's 2 tracks, and it's basically this area right here. There's an area at the top and the bottom. And there's on this over here, right here and here. There are ball bearings. There's tracks that run around the inside of these rings. There's balls in there, and then those balls cause it to actually turn and actually rotate and go smoothly. However, it's not 100% smooth. They're a little noisy. Sometimes they got jammed. We always had problems with ball bearings. They're not always the perfect shape. So sometimes in manufacturing, they actually didn't even come out right exactly. The bottom is called the fluid dynamic bearings. So that's actually what we're replacing here. So that's the actual part that I'm going to be talking about. This is a picture from IBM. This actually has to do with how fluid gets in there and how they actually keep the pressure even. So that's what we're looking at. So what's the problem? What actually happens? So what actually happens is while your platters are spinning, or even sometimes before they're spinning, there is a seizure. And so basically that pin in the middle, that picture that I had to really beat the crap out of to get that pin out so that I could actually show it, because it was completely jammed. It was not moving or fluid at all. So that area that's getting red there, basically what happens is it heats up, and there's a reason it heats up, and there's actually a reason for what actually happens in there, not just the fact that it's spinning, but it will actually just seize. It'll basically cause it to be, you can't turn it with anything. It's impossible. I mean, I've tried it with just about every hand tool, that you can possibly do to get this thing to move, and it will not move. So once it seizes, you're dead in the water. The easiest thing at this point is either try to figure out a way to get it moved to another set of platters, or get rid of this spindle itself and get rid of the bearings themselves. So this is what it looks like. So the fluid dynamic bearings, basically there's a lot of math that is behind this, and you guys will love this part. Basically there's a fluid at the bottom, and the fluid actually gets sucked up the shaft. And so we'll actually... So that's the part that makes it dynamic. Basically, what you're talking about is there's some grooves that are cut in the inside casing of the center portion of the spindle. And those grooves that you're actually seeing there that are in different directions are done so to increase pressure and to increase flow. So viscosity is basically the measurement of the fluid against resistance. And then that resistance actually causes the material to be sucked up the shaft from the base. So that's actually what's causing the bearings themselves to actually flow smoothly so that the center pin will turn. And so when that doesn't happen, so for instance, let's say cold temperatures, and you turn on your drive, and the fluid is much thicker than it would be normally because it's cold. You may not get the proper spinning rotation of this drive because the fluid it may take a while for it to heat up to get to where it needs to be before you actually have it inside the grooves inside this. So I'll try to show you a little bit better. But one of the reasons they switched to fluid dynamic bearings is they're a little easier to make from a standpoint of, you're no longer dealing with ball bearings, which are inaccurate. It's a little faster. You got a lot better shock resistant. There is a little bit better heat and a little bit better control there. However, again, as anything, when you're dealing with a cold hard drive or something like that, it may not spin up depending upon what the temperature is. And it also decreased the noise quite a bit to the point that you almost can't hear a drive anymore. And the only type, because somebody might ask what kind of oil is there, IBM at least documented the kind of oil that they had, and it was called ester oil, which seems to be very similar to like 3M or something like that you might have in your car. Yes, sir? Yes, that's in noise, yes. -4 decibels. So this is what it looks like inside. If you can see those little grooves in there, those little grooves are actually what causes the fluid to go in a particular direction when it starts to spin up and then get sucked up that shaft right into the middle there, which actually is what keeps it basically lubricated so that it can spin and then it can turn. This is a picture from one of the engineering slides from IBM about how that groove actually causes the difference in pressure. You can also see a difference in heat. You can see what it might actually do with regards to jamming, or how it might jam, or what might cause a problem with that if the fluid didn't get there, or over time maybe the fluid kind of dissipates. So those are the kind of things that actually cause us a problem that we're trying to deal with. So this is a quick overview, you'll see this one again, of how I basically think that I'm going to remove the spindle component to remove what's trapped in between the platter assembly and the drive itself. So this is kind of giving you that overview of, we're going to basically punch through the bottom, we're going to capture the platters, and we're going to get them free of the base. And then after we get it free of the base, we basically need to get this bearing out of the middle, and I'll explain this piece again in a minute. But basically, I need to get the bearing out of the middle of the platter so that the spindle is still intact, so that I can actually get that component out. So I'm going to use a drift, basically, to punch that out and to get that free. So this made it look really simple and really easy, but it's really not. So let me explain how this actually happens. This is the goal. This is what you're trying to break free. As you can see there in that little center ring, there's a lot of epoxy and stuff that's in there. And basically, I'm using a 1-ton press in order to get this thing to pop out. So it may be a little easier with a 2-ton press or a 3-ton press, but I'm using a 1-ton press and I'm getting this thing out. So it's epoxied in there pretty good in order to actually get that thing to break free. So this is the first goal, is that you want to do this, obviously, trying not to do any damage to the platters themselves. So my first thought was, when I'm trying to design a tool, what could help me punch this out? What do I have that's the same size? Some of these other higher-end tools, they milled parts, and they had all kinds of things for sliding and pushing the whole thing and trying to get the exact same size. And the first thought I had was, well, how about another one of these? What if I just popped one of these out, and then I used that as the tool and put that between the arbor presser? It would be basically the same size, and press that down and actually pop that out. So that's kind of the steps that I'm trying to take. So I'm going through this component. So basically, this is the goal. You'll actually see right there around the outside ring, this is actually a magnet right here on the inside of this component here. And then that's actually just popped through the top of that lid. So I'm going to try to pull that out. But this is the goal that we're trying to get to the bearings. And then through the top, we're actually going to have to then worry about using a drift and try to punch this through so that we can actually get this off the top. And then this is what it'll look like once we're empty. Now, in this case, once I've actually gotten to this spot, I now have the client's platters ready to be moved to something else. So I'm going to go through the 3 steps in the process of what it's going to take. This particular item right here, IBM documented this as what they call the stator. And so the stator itself basically is what you're actually applying the power to. Now, it turns out that once it's in the drive, it kind of also makes kind of a good area to hold the platters once they've fallen out of another drive. Because you need something when you're pressing down that you can actually hold underneath it that catch the platters. And so you have a couple of choices, build a box, find a box, do something, but I'm putting 1 ton of pressure on this. So the easiest thing for me to come up with was, why don't I just use another drive? Use the whole base of another drive and actually try to cut this out so it'll actually fit in that space, because it's already kind of that same exact size. And so this particular component will actually hit the top of the platter assembly and not touch the platters themselves when I'm actually pushing it through. So when I've tested this, what I did was, I need one of these things first. So you don't have a way to remove this thing unless you just beat the crap out of it. So initially, I just got a punch, and I just stood there with a hammer, and I beat the crap out of this thing till I get one of these things free. And this is a junk drive. So you're going to take a bad drive, and you're going to beat the crap out of it to get it all into parts. And so obviously trying not to do as little damage as possible to it. And once you've actually popped this thing free and you get it out of this casing, you're going to have to remove this component from the top piece, as I described earlier. So the next thought I had, well, again, I need the same kind of thing. I need some place I can punch this thing through that would be the same exact size. So what it turns out is, if I just took the same dummy drive that I had, and instead of trying to go and mill out some other part again, if I just flip it over and I drill this hole out a little bit bigger, the same hole it came from in the junk drive, that it'll basically be free and clear. It'll actually pop through. And the ring that is on the bottom of the platters themselves, where the magnet and everything sticks through, is way below where the actual platters themselves are and the data is physically stored. So all I have to do is drill out this hole a little bit bigger. You can see another silver ring around it now where I've put one on top of it. And basically, I'm going to take this piece, make sure it's nice and smooth and will fall through there. And then once it actually falls through there, that ring on the bottom will keep it right there on the top of that ring without hurting or damaging any of the components inside. So I'm running through kind of the diagnostics process of this at this point, so I'm beating the crap out of drives and doing this over and over and over until I get the sizing right. So it may take you 2 or 3, but it turns out, obviously the same exact drive is going to be your best option to use, and you'll be able to kind of get this ring, and you'll be able to push it out. So if I take the drive, I flip it over, I put it in an arbor press, and then I take a drift punch. Now, I went through a few pieces, and I don't remember the exact size right now, but I basically bought like a drift set that had a whole bunch of different sizes in it for $30. And then I just went through them until I found the one that hit the exact size, and it would actually sit in the middle of that pin. And then I'm able to use an arbor press and punch that through. And you'll see the bottom of the drive flipped over. So I'm actually using that as my tool on that bench press now. And so I'm going to push that through, and then once I've pushed it through, I then have it free and clear. It'll just fall out of the base. So now I have my bad one. I have the one that's beat to crap. So it doesn't spin by this time. It doesn't turn. So this is not the one that you're going to use to actually put in a good drive, okay? So this one's not going to function. So, but the problem is that on the Arbor Press 2, I can't really push down on that pin itself, the nipple that's kind of sticking up right here. If I push down on that, it's going to cause other problems inside. It'll bend, like a nail or whatever, and I won't get a flat surface. So at this point in time, I actually go through the process of cutting it off. Now, so you cut off the nipple.
Only you could make her talk about hard drive sexy.
Woo! So once you get...
Nipples is sexy, that you're the only one that was talking about the shaft earlier.
That says a lot about your sex life. Hey, Robin, how are you? So basically, you're going to cut this. All right. Okay, fine. You guys saw that DEF CON speech where I did the data recovery for RAID with porn on it. Did you guys see that one? And I'm sitting there and there's like sounds of people sucking, and I'm sitting there going, I didn't know that actually. Anyway, all right. So the center pin, we're going to cut the center pin out of the spindle here, and we're basically going to, and I'm using a $25 saw. Now, I went to Harbor Freight, and I just found the cheapest saw that I could do that was automatic, so I didn't have to keep using a hacksaw. The issue here is you're going to need two areas to work in. You're going to need one that's a clean area that when you get to your client drive, that you're going to be able to keep your platters and everything as smooth and as clean as possible. And you're going to need one area where you're going to do all your manual stuff. You're going to beat the crap, use your Arbor Press, do all this stuff to kind of get it working. So you kind of have to have these two areas. Now, again, we're not talking a lot of money. We are talking a lot of practice. We're talking, 6 hours of practice on 2 drives to kind of get this working so that you can actually do a replacement. But once you got that done, it sure does beat $6,000, and or sending it off to some data recovery company that might cost you $2,000 or whatever. So in this case, I've got a $25 saw, and basically you'll see here down at the bottom, I've actually taken in the vise, and I'm actually putting the bearings themselves, and I'm going to cut off the end of the nipple there. So that's where I'm at with that. Now, once I actually have that done, it's a perfect fit. It's flat on the top. It's got a perfect fit over the top of the base, and I can use this thing over and over and over again to pop out spindles and break free of that particular epoxy and where it's stuck. So this is basically what I've come up with for my tool set. Is $100 worth of stuff: a hammer, a caliper, some punches, and now I've got 2 drives at this point in this particular one, and I've added some clamps. And it doesn't matter what kind of clamps you use at this point, but they just have to be strong enough to hold 2 drives together so that they're aligned perfectly. There is a lot of detail in doing the alignment. I'll get to that in the client drive. So again, this is the plan. This is what I'm going to try to do. Now, in the process of trying to get this so that it pops out, in the drive below it, in the parts and pieces that I'm using for the toolkit, I kind of have to Dremel out all the pieces that would be in the way. So in your dummy drive, when you're making it, and you flip this thing over, the pieces are going to be in the opposite order when you're actually trying to drop them into another drive. So you have to take a Dremel, and you kind of have to go around the whole inside of that drive, cut off everything to make it square, so that basically the parts or whatever, or cut it so that it actually fits correctly, so that when the drive falls upside down, it falls smoothly, and that the top of that piece of the platters that actually has the spindle component on it hits the stator, that it sits on top of the stator itself, so that it doesn't touch the bottom of the drive and it doesn't leave a ring or go in any other direction. And because they are that same exact size, it's kind of like a straight transfer. If you cut it out, they'll actually fit into the grooves properly, and it won't twist and it won't turn. So that's what I'm looking at here. I've popped it out, and I've gone through and I've cut out and I've made the edges. It's really dark on this slide, but it's cut out and the edges are all cut so that this is now upside down. The platters are completely upside down in this particular component. And so I'm looking at the fluid bearings, and I've cut it out so that it actually fits properly. Okay? No, this is still the practice, the beat-up drive. I need to get a good motor, a good spindle, a fluid bearing from a good motor so that I can actually, I'm sorry? Yes, this is my landing pad. So I'm basically trying to do what I can. See, there's the stator at the bottom. Again, that's bright on my screen, but it's not on the projector. So the stator's down there. This is upside down, and the top is actually going to sit on top of that. So it's not going to go beyond that. It doesn't hit the edge of the platters, and it doesn't cause any problem. But you do have to practice with this, cut the pieces out so they fit appropriately so that you can actually get that done. And so then that's where you'll actually be at this spot where you'll now have this piece. Again, taking the junk drive, and I'm able to drill out this hole a little bit bigger. So this is not the client drive still. This is still the one that I'm trying to remove a good spinning fluid bearing from in order to replace the fluid bearings in a client drive. So at this point in time, it'll actually just fall out the bottom once you actually get to that component. It'll actually just fall right out, and then you'll be able to use this piece to do your final component where you're actually heading into your client drive. So now, we've done this process twice, is ultimately what we're looking at. So we have two now. We have one that is the beat-up one that has the nipple cut off of it. We have a second one, which is now from a working donor drive. You don't need anything else but that spindle, the spindle bearings themselves, in order to replace them. So now you're going to go to your client drive. Now this is where you're going to need some air. You're going to need to have a clean area. You're going to try to do everything you can to try to not touch or do anything with the platters themselves. Now luckily the spacers that are kind of around it, you can use those to actually hold the drive, to flip it over, to do things. And obviously you can wear gloves and do the appropriate things you would as I've given in all the other talks. Because you already at this point have had to remove the head assemblies. You've already had to take all of these other things and do the appropriate things with the electronics and removing them, getting all the screws out. So we're looking at how we're going to actually now replace this particular one. Well, you have to use this caliper. So this is one of the first times I've tried to really introduce taking a lot of measurements in the drive. In order to actually get the platters at the appropriate height, you're going to have to take some measurements from both that center pin and from the bottom of the drive and from the head assemblies, because your whole point is to get the head assembly to match up with the exact same height of the item that you're replacing. So I have to use a digital caliper, which I paid $15 for, basically. And what I'm using in the digital caliper is down here on the end, you see where there's actually a piece of metal that slides down? I'm not using the component at the top where I'm measuring between two distances. I'm using the pin that they have through the bottom so that I can actually measure height and distance. So this is what I'm doing. Turns out that the bearings at the bottom of every drive are not at the same height. They are all at different heights. So sometimes they'll be further in on a drive, sometimes they'll be higher up on a drive. Sometimes they'll be sticking out and protruding in a negative direction, and the other times they'll be in a positive direction. They are always different. They are not the same. So you have to take a measurement and write this measurement down and track it from your source drive. You basically want to make sure that you're getting it back into the exact same position. So this is one where you'll see that it is actually sunk in a little bit. So the actual bearings themselves are further into the drive. And so I'm having to measure those to make sure that I'm going to reach the appropriate height. I can't just push them back in and hope they're going to be at the right height. The other thing that I've actually gone to is measuring the heads and the head assembly itself. So I'm actually able to do a little bit more accurate, even from my previous stuff of doing a head replacement, by using a caliper to take the measurements of where the head assembly is. And so I usually will take two measurements now. So you guys should recognize these things I've done in other talks before, where I physically am making a foil tool. And so I teach a class on how to actually do this and go through the process. I have a 5-day class on replacing head assemblies and going through this whole thing. But what we're looking at here is I'm protecting the heads. I've got them right at the edge of the platter. I'm taking two measurements, so I've got one line here and one line here. I'm measuring the height of them before I remove them. So because I do it in two areas, in two locations, I can keep it level. And so you can take as many as you want, actually, at that point in time, but for this one I did two. And so this is my disassembly component. You'll actually see the screw right here at the top, which actually is the part that will remove the head assembly, and I'll have this clear of the drive so that I can deal with the platter assembly. And then I'll go through the part of actually popping this thing out. So this is where I clean everything, clean your arbor press, you clean the area itself, and you have to have some filtered air or something that you can, there's a number of ways to get filtered air, but for the do-it-yourself, or maybe you're just using, some filtered air or something you got from Home Depot or something. So at this point, basically I'm going to pop out with the arbor press that one pin. And so this is how I hold it together. Basically, I've dremeled out this bottom one. There's actually a bottom drive down here. And so the bottom drive is aligned perfectly. I need both edges to be aligned, so I'll clamp them from both ends. One other thing that you need to pay attention to is your arbor press itself, whatever you've got it mounted on, and wherever you're using, I don't know if people know what the arbor press is, I got a picture coming up, but basically it's just a press, it's a $40, $50 press, has an arm and a lever, and you pull it down, and it basically looks, kind of like an anvil at the bottom, and you have an area that you can work on. Well, that area needs to be level. You have to deal with level stuff because all your measurements are going to be important here. So when you actually put the drive down and you do everything, you basically are leveling it to make sure that you're able to do it smoothly and on a flat surface. And so I'll actually clamp the two together, the two hard drives together, make sure it's all clean and the Dremel, there's no Dremel, dust sitting around anywhere. Clamp them together, and then once you line it up, you're able to press this out, making sure that you actually have all of your stuff level as it could be. And so this is actually the process at this point where I've actually clamped on both sides, clamped everything down, leveled it up, and I'm popping the piece out itself. So you do it in one smooth, fluid motion, and when you pop it, you're going to hear a little bit of a pop. It's going to, just going to kick like that, and then the actual platters will then fall down below. So this is it in the client drive. So the top one is the good one, the one that I'm going to end up putting everything back in. So this is what has happened after I've popped it out. The other one's sitting in the bottom drive that I've cleared. And so I'm going to flip that one back over and protect it and keep it out of the way, keep it covered while I'm working on getting the spindle, the bearings free, and then putting all of this back and assembling it back together. So again, I'll go through the process of popping out that center pin. This is what I'm using for an arbor press, if you guys have seen one of these before. So ultimately, this process has to be done 3 times over and over and over again, practicing, trying to keep it level, do everything you can to try to make it as smooth as possible, clean your area, and clean up all of your fillings, your Dremel material. When you go to put this stuff back in, you're actually going to do it in the opposite order, but now you've got to worry about those measurements. You've got to worry about how far up and how far down. So my suggestion here is to do it lightly, a little bit at a time. So basically, you're going to take your fluid bearings, you're going to put it back in your original platters themselves, back in the center. You're going to pull down gracefully, trying to keep it just enough in, because it's harder to back them back out than it is to push them back in. So you gradually move 1 millimeter at a time is basically what you're looking at. So when you're dealing with your caliper, you want to get as close to 0.3 millimeters off as possible. So that's really what you're kind of heading towards, is trying to make sure that you're so exact. 0.3 millimeters is not a lot of space. So when you're actually pushing them back in, you need to take a measurement from the top with the hole, and then you've got to take a measurement from the bottom once you've put it back in. This is what it looks like from the side when you're actually pressing that back in. So you'll actually push that back in directly into the assembly itself, and then you'll flip it back over and push it through on the bearings, and then you'll take a measurement again here. Now, at this point in time, once you finally have wiggled it back into space in the same amount, you can apply epoxy to it to hold it in place so that it will function normally. Or at this point, I've actually found that they actually will sit there just fine, and maybe I can break this one apart after I'm done with this one and use it for another recovery. Once I've moved the data to another drive, I no longer care about this, but I've still got to go through the rest of my reassembly. I've got to go through the head assemblies and all this other stuff, so it's better if you epoxy it back into place. So this is the basic epoxy that I've been using to do this, super glue. It's the super glue epoxy. It holds it well enough for the drive to function and for me to be able to complete my process. So, and this is, again, in addition to all the other numbers of things that I'll actually do. So that's my process, and that's how the bearings are working. I'll try to smooth some of the things out and republish some more animations and things later once I get that piece down. But ultimately, you're able to build all the stuff out of the same tools and not have to go and spend $6,000 or $12,000 on something to get it done.
But
So.
Scott, won't the $6,000 tool work better?
The $6,000 tool will do it exactly the same way, basically, except it will cost you $6,000. It will be a little cleaner because they have milled all their parts, and so the parts that they'll actually have will solve some of maybe the measurement problems and things going back and forth. It doesn't solve any of the other problems with head assemblies, any of the different motors, Western Digitals, anything. This is basically the process that you're going to end up having to deal with over and over and over again, regardless of how much you spend. So, any other questions? Yes, sir.
With the circuit board replacement, you have to be very precise about the model of the drive. You have to be as precise for the bearing. Generally the same model.
Yeah, you want to use the same model of drive. You want to use the bearings are sized according to the models. So you do have to, the question was, do you want to be as precise on the replacing the fluid bearings as you are with the electronics? And you do. You have to use the exact same model to actually accomplish the job, or the size will be different. You won't be able to function with the size. Any other question? Yeah. Yeah, this will be, as soon as I get back, I'll publish this stuff on the website, and then as I make changes to it, adding more additional material to it, it'll be up there. I'll put it up. Thank you. Thank you. How common is the seized motor problem? On newer drives, it's becoming much more common. On older drives, it tended to be you could move the platters and not really have this problem to deal with. But on all the newer drives, 500s, 1 terabytes, 2 terabytes, 3 terabyte, all of those, they're almost, 10% maybe at this point are seized motors. Yeah. Yes, sir? Yeah. Yeah, it does eventually damage. What happens is basically the parts can contract. So like any place that you have like a chip that may not be contacting the board correctly, when you freeze it or whatever, it'll either pull the head assembly back or pull a chip to it or something along those lines. So
So it didn't have anything to do with the fluid. I thought maybe somehow the fluid would be frozen.
not really from that perspective. Typically, I would think that that's going to be the worst of it. It depends on if it's a problem with it spinning, you can hear it. It usually whines and screams. So.
Yeah, that's exactly what it was.
Right. Okay. Yeah. I mean, any change in temperature will cause it to contract and expand, and then you'll actually get some movement out of it you wouldn't get otherwise.
How much does your company charge, like, let's say, gravity?
On a standard recovery, we charge $800. Yeah. Mhm. Well, it may be one of the things. The issue, obviously, with a drive that's not functional or working may not necessarily be because it's not spinning, or it may be having a lot of noise when it's spinning. But any kind of metal contracting or expanding may allow that to work, and that's why when you freeze it, refreeze it over and over and over. But there's also some electronics and head problems that actually are fixed sometimes by freezing it, which is, if you have a chip that maybe over time is, contact isn't good or whatever, when you freeze it, it contracts. And so you may have a chip that's now contacting where it didn't before, or a head assembly that's actually stuck to the platter based on something called stiction, and it pops off, and so it'll actually be free at that point. So there's a lot of things that kind of freezing it might help or fix. I agree. Unless you have no other choice, it should be a last ditch thing, because basically at that point you are going to physically start doing damage to the drive, and all this contracting and expanding of the heat and cold is going to cause physical problems at some point. Eventually it won't work. If you've done it enough, you'll know eventually it won't work.